Hello, am I here audible? Am I audible?
Yes, sir.
If someone should answer, man. If you have not read, just say no. Complete blank thing is completely useless. This is not how things happen. So, by the way, how many of you are already in campus? Hello. Hello.
So I am in campus.
Okay, at least someone told it. How many? Okay, maybe I need to really. Okay, can you see this poll? Okay, so only 4 of you are in campus. Excellent. The other thing that I really need to know is, are you guys a MTech or GRFC? Okay, 50-50. Good. Okay, so since I'm not getting any answer from you when I asked whether you have done it or not, so I'm assuming that you have got understood the whole concept of planarity. Because if you had not, then you'll ask me, right? You guys have no doubts about planarity, right? So let's see. Indrani Locha, are you there?
Yes.
Yeah. Can you prove to me why this one is not not planar?
There is a criteria for a graph to be planar. I read it earlier, so I didn't read it right now. That was some formula like v minus e plus f is
Okay.
equal to 2 or something like that.
Okay, so you've read that. Okay. Lakshmikant Shah, are you there? Hello. Okay, connection doesn't seem to be very good. Well, Monideep A.
Yes, sir.
Yeah. So did you try to prove this whether this one is planar or not?
No, sir, I did not try.
You didn't try.
No, sir.
And you didn't even tell me when I told you whether you read this concept of planarity or not.
Yes, sir, I will.
Why? I mean, you don't care, is it?
No, sir, I thought, I mean, since I just have not read, I don't have any doubts, so I thought it's not necessary. Like,
Okay.
Sir,
Nirup, yeah. Yeah.
sir, if we are not familiar with that formula, v minus e plus f equal to 2,
Yeah. How do you prove it?
yeah, I mean, for every intersection, do we have to try to redraw the graph or something?
Exactly. So the reason I asked you guys to try to prove it is because it is easy to convince yourself that it is impossible to draw using in a plane, but proving that this one is not planar formally is actually not that easy, because you cannot just keep on drawing. Sorry, something happened. Hello.
Yes, sir.
My screen got switched off, is it?
Yes, sir.
Yeah. So that's why. So I just wanted you guys to try it out so that you guys see that why this is a hard thing to prove if you don't have a understanding of I mean, how do you kind of go about proving this not mathematically or formally? So let's start with, okay, a particular properties. Let's start with some properties of planar graphs. Okay, the first, so in a normal graph, they have basically two concepts, right? They are the concept of vertices, two parameters rather, and there is this concept of edges, right? Now, but if I give you a planar graph, now only for a planar graph, right? And somebody gives you a drawing of a planar graph. Okay, so I give you some particular kind of a drawing, right? Maybe something like this. Something. Now they also have this concept of the third thing, which is called the faces. Now, what is a face? A face is basically, okay, a face is basically a space that is surrounded by a set of edges. So think of this one as fences, okay? This edges being some kind of a fence. Okay, this drawing the fencing on earth. Okay, on the ground, someone has put up fences. This edge, each edge is a fence. Okay, in that case, we can talk about, okay, so this point is here, there's a point here. Now, these 2 points are within the same fence, right? So they kind of are, you can think of it this to be a single country, right? But if I take another country over here, now this country and that country, so if I have to go from this country to this country, I have to cross this line. Okay, I have to cross it somewhere. Okay, now, so this kind of gives us the concepts of faces. Okay, so like here there are 1, 2, 3, 4 face, and also a face outside. Okay, so this has 5 faces. Why 5? Because this basically says that, okay, I mean, take any other point in the whole space, in the infinitude space. Okay, then there is exactly one point from which it is connected. Say I have a point here, then that is connected to here, right? Or I have a point here, then that is connected to here, and so on. So the concept of faces is something that we have in the case of planar graphs. So these planar graphs have 5 faces. Is this clear? Is the concept of faces clear?
So
Yes,
could
sir.
you once repeat the concept in terms of paths that you just said?
Okay, so let me tell you that 2 points are in the same face. If there is a path from one point to the other, okay, path meaning path in the R2. So we are always talking about in terms of R2, right? So I say that, okay, this point and this point are in the same face. If there's a path that kind of connects this point to that point. Okay, now this path does not intersect any of the edges. Okay, so similarly, there's a path from here, there's a path here. So this point and this point are in the same face. Okay, so there is a path from point A to point B that doesn't intersect any of the edges. Fine. So that is the definition of the when 2 points in the same face. Okay. Now question is that how many different faces are there? So you can think of this equivalence relation as point P is related to point Q if there exists a path from P to Q that does not intersect the rather to say the edges or any edge, right? Then this is this is my definition of this relation. Now you can prove that this is an equivalence relation, and in this thing the set of the equivalence classes are the faces. Okay, so basically a planar drawing, not a graph, a planar drawing of a graph splits up the whole space into some number of faces, partitions the whole space into some number of faces. Is this clear? Hello?
So
Yeah.
the vertices of the graph are in R2.
Yes. Yeah. So you should not think of the vertices. Think of the vertices just as some very small points. So vertices is not the problem. Okay. So think of this. Yeah. So I mean, when I mean points outside the edges and the vertices. Yeah. The vertices are not in R2. Vertices are embedded or drawn on R2. Is it clear or something? Is in doubts, Omkar?
So I am actually not able to visualize the graph drawn on R2 actually.
So look at this one. I mean, forget R2. So this graph, right? Okay. Now this is a planar graph. Why? I can draw this planar graph in this way. Okay. So I have these vertices and I have the edges connecting them. Okay. Now R2 is nothing but the plane, simple piece of paper.
Oh, okay. Yeah, understood.
R2 is just a two-dimensional plane.
Yes, sir, understood.
Okay. Is it clear?
Yes, sir.
Any other questions? Hello. Is there anybody who comes from the who have done an undergrad in math?
Yes, sir.
Yes, sir.
Okay, so there are some people who have done undergrad in math, right? Good. So I have just told you. So the definition of faces are there, right? Any doubts on definition of faces? Any problem with the definition of face? Okay, so let me tell you one very simple, interesting thing. Okay, in the definition of faces, one important thing I kind of assumed is that if I draw this thing, right, there I have how many faces are there? Can you just tell me how many faces are there in this graph?
2, sir.
2. Why 2? Why 2?
One inside and another is outside this box.
So you're saying one is inside, one is outside, right? And the reason these two faces are different and not a single face, because if you draw up, if there exists no path from here to here, that does not touch this. that does not touch this space, right? Edge. Correct. But you know that mathematicians are a bit crazy. Actually, this fact, the fact that a circle, or the fact that the number of faces, or maybe let's put x, fact that there does not exist a path from x to y that does not touch the edges. This is an obvious fact, right? Hello?
In artificial, obvious.
It's an obvious fact, right? Actually, my dear, can I maybe try out a different thing? Can you, all of you, keep your things unmuted? Can you please, all of you, keep your thing unmute? That will be much easier for me to talk to you guys. Okay, and please shout out whatever you want to say. Okay, don't worry out. Okay, good. So you all agree that this is the obvious fact, right? But actually, to a mathematician, this is not an obvious fact. So to a mathematician, this is not an obvious fact. In fact, this fact actually requires a proof. And that proof is what is called a Jordan curve theorem. And proving this fact is actually very hard. It is actually not at all easy. Okay, the proof is using the concept of algebraic topology. Now, of course, I will not go into algebraic topology right now. But I will try to explain you why this fact is not as obvious as you think. Okay? So you told that this is so you told that this fact is obvious, right? So in other words, what I can say is that, say somebody comes and draws a big line like this, a circle, it has two parts. There's a part with inside and outside. They are not reachable from one another. Right? Right? It's not reachable from one another. Now, how do you, why is it not reachable from one another? Or say you are standing here. So think of it this way, okay? Think of it this way, that you are standing here and your friend is standing outside, okay? And there is a friend is here, okay? So this is you and this is your friend. Now, so what you are seeing is that this is a curve over here. This curve is something that is drawn on the ground. Okay, fine. So think of it this way, that you are standing in a particular place in the world, in the earth, in the round sphere earth, and somebody has drawn a big circle, something like a boundary of a country. Right? Something like a boundary of a country is drawn there. And then you are saying that, oh, this boundary of a country would say that there is an inner one and an outer one. But think of it, you are a very tiny person, right? And in that, what you are seeing is that a boundary, a kind of a boundary that is far away, right? So you don't know how is this space. Are you standing? Maybe you are standing in the circle. Okay, so maybe this is the earth. Okay, this is the earth, and you are here. This this is possible, right? Fine. To you, it looks like this. But it also can be possible that you are standing on something like a tube. Maybe I should not draw this one. I should have this is the boundary. And you are standing here. And your friend is standing outside. Now, in this case, do you think you can reach your friend
Yes.
without crossing the curve?
Yes, sir.
You can, right? You can go from here on the other side, and you could reach there. So suddenly you realize that the fact that this curve separates it into two parts so much depends upon where it is drawn. Is the
But I
earth, sorry?
I didn't get it. How can I reach, like, I'm still crossing the inner part of the tube, right?
You are going, so okay, I will not cross the boundary.
Inner
Okay.
boundary I am crossing.
No, you are not. How? You start from here, you go there. It's like a tube, right? You go from the other side of the tube. Other side.
I am crossing the red boundary, right?
No, you're not. Okay, maybe it's because of my drawing that is happening. Okay.
Is
Okay,
it three
think of it this.
dimensional?
It is three-dimensional. Okay. So this is, do you understand what is this? This is a vara.
So
A
donut.
It's a donut. Do you get it? It's a donut shape.
Yes.
Okay. Now in this donut shape, there is this boundary wall which is on this donut shape here. Okay. Fine. Now you are here. Okay. Where are you? You are somewhere here. And your friend is somewhere outside. Okay. So you can just go to the whole of the donut, go on the underside of the donut.
Yes, if
That
it
is
is
not
three dimensional.
Yes. So that means whether, I mean, in the three-dimensional, you are pretty fine when I talked about this thing of sphere, right?
Yes,
But as soon as it goes for torus, this is called a torus. It is not true. Okay. So now you see any mathematical proof that says something like this, that you and your friend have to cross this boundary wall to reach each other, that depends on the surface on which it is drawn. Okay.
Yes, sir.
So this is not at all an obvious statement. And that's why the mathematicians have spent a lot of time proving this. This is one of the most celebrated theorems in mathematics you can think of. It's called Jordan curve theorem. And the proof is not at all easy. Okay, so anyway, so this was a bit of a detour. The reason I told you a detour is that if you look at the books, many of the books will state this statement, Jordan curve theorem. The reason is that without the Jordan curve theorem statement that we have, none of the things that we are going to say, even including definition of phase and all, is a correct definition. Intuitively, everything makes sense. But the very fact that I told you this statement, okay, and this is this is what is kind of what I am kind of drawing, or the simple thing that this particular thing has two faces is something that is depends a lot on the Jordan-Kurth theorem, the formal proof. I will not go into too much into details of Jordan-Kurth theorem, but remember that there is, whenever people want to work on planar graphs, the Jordan-Kurth theorem comes in the picture.
So,
yeah.
But even in the other case, like the sphere inside, like the left side figure, then also you can go inside the earth, and if it is three-dimensional, you can
No, but it is a sphere. It's an earth. It's
yes,
an
like
earth.
you can go inside the earth and reach there.
You can make a tunnel, you are saying?
Yes, tunnel.
No, I'm not making a tunnel here. You realize that. Here I'm not making a tunnel. Think of it, the earth. Okay, what happens if the earth was just a tube? Right? So to start with, you have that, okay, there is an earth on which if I draw a fence, there is something called the inside of the fence and outside of the fence. Right? In the world, in the globe.
Yes.
But if the globe was not a round sphere, but was actually a tube, you could not have told the same thing. It's not about, I'm not making a hole or something here. Okay. The space itself, just imagine that the world is not round, or you are in a planet which is not round. The planet is a donut-shaped object. Okay. And all I'm trying to say is that it is not obvious. The very fact that a boundary splits up into two parts, the inner part and the outer part, is not at all obvious, unless you take into consideration what the object on which it is drawn is. Okay.
Yes, sir.
Yeah. Okay. If you are confused here, I mean, I can imagine this can be confused here, so don't worry about it. I mean, it was kind of a detour in which I wanted to just tell to you that the importance of the concept of Jordan-Kurth theorem, and why to formally prove whatever we are saying, you need something like a Jordan-Kurth theorem. But most of the time, intuition will be good enough for proving things in the case of planar graphs.
Sir, one more question, sir. For
Yeah.
that square figure, that square figure, the square figure.
This one?
Sir, yes, sir.
Yes.
Sir, XY. Sir, there does not exist a path from X to Y that does not touch the edges. Okay, but does that necessarily mean number of faces will be 2? It can be more than 2 also.
Very good point. It can be more than 2. How? I mean, a good way is that, so maybe this is something that you are asking, that is there a unique number of faces? So for example, I have given you this graph, right? And somebody comes up and told that, oh, see, this is my drawing. And you can show that, oh, see, this is actually a nice drawing of this graph. Very good. Somebody comes and says, no, I will draw it like this. Now, this is also a nice drawing of this graph. Are the number of faces same in both the cases? So here the number of faces, it is 1, 2, 3, and then 4. Here it is also 1, 2, 3, and 4. Okay, here number of faces are same, but is it necessary that every drawing of a graph have the same number of faces? So does all the to all the planar drawings of a planar graph. Have same number of faces. Now, this is a very important question to ask. Okay. And actually, the answer is yes. However, you might be able to draw a particular graph in many ways. They might look very different. For example, this graph and this graph might look very different, right? This graph and this graph in one shot doesn't look same. Both of them are planar graphs. I mean, just maybe if you are not convinced that these two graphs are same, 1, 2, 3, 4, say 1, 2, 3, 4, and 1, 2, 3, 4, you can see that they are the same adjacency matrix or adjacency. Okay, if the edges are exactly same. So there can have multiple drawings of a planar graph. Many drawings of planar graph, I think. And but all of them will have same number of faces. In fact, this is the next thing that I am going to say. This is a very famous formula. It's called the Euler's formula. Is that if G is a planar graph, then number of faces equals to number of faces. So number of faces F is equals to, short second, E minus V minus
plus 2.
Plus
yeah,
2.
plus 2, right? Plus 2. Yeah, plus 2, right? Plus 2. Okay, now, okay, let me try to see how to prove it. Okay, let me give you a proof of it. Then this is a very important and beautiful concept. Okay. Now, before I prove it, I want to just, so this is a proof by induction. Okay. And by induction on what? On number of cycles. Okay. So first of all, what is a graph without any cycle?
Forest.
Tree.
Oh, sorry, I made a mistake here. Number please, not a planar graph, but I have to have a connected planar graph. Okay, is a connected planar graph. Yeah. Monidip, are you there?
Yes, sir.
Yeah. So can you tell me a graph that doesn't have a cycle?
Yes, sir. We can draw any tree.
A tree, right?
Yes, sir.
So any tree doesn't have a cycle. Now, how many faces are there? Okay, how many edges? So if I have a number of vertices in a tree is n, what is the number of edges in a graph, in a tree?
N minus 1.
It is n minus 1, right? And what are the number of faces here? See, by the way, this is a planar graph. You are right? Because easily one can draw a tree in a way that it doesn't have an intersection. Right? So what is the number of faces in a tree?
1.
It's 1, right? Sorry. So V, E minus V plus F is equals to, sorry, I made a mistake again. It's E minus V minus E, right? V minus E plus F is equals to 2, which is exactly what you can see here. So F equals to 2 plus E minus V. Okay, so this is the base case of an induction. Okay. Now, how do you go ahead for other things, right? We start with the graph on with ages equals to E, say ages equals to M, vertices equals to M, a planar graph. Okay. Now, first of all, let me ask you a very quick thing. If somebody draws me a graph, right? If somebody gives me a planar drawing of a graph, okay, and if I take any edge, so I take this edge and I remove this edge, will that graph be planar or not?
Yes.
Huh?
Yes.
The graph will be planar, right? If I take any edge and I remove it, the graph will be planar, right? So if G is planar, because we have got a planar drawing, then G minus E is planar for all edge in the H set. Good. Another thing, this is the first observation. Another thing, and maybe who can answer me this question? Let me see. Priyabrata Mondal, are you there?
Yes, sir.
Yeah. So what happens if I take a edge that is a part of a cycle, right? And I remove that edge, right?
Yeah.
How many? Okay, first of all, how many faces does this edge participate in?
Two faces. So one face will reduce if we remove a edge from a cycle.
Correct. So if I take any edge that participates in a cycle, so not this edge. This edge, for example, does not participate in a cycle, right? But you take any phase that participates in a cycle, that means they have this cycle. It must have another phase that is associated to it. Say, for example, this phase, this edge participates in this cycle. But if I remove this edge, then this outside point and this point will kind of become in the same phase, right? So if I remove this edge, then the number of phases will go down by 1, right? So if E participates in a cycle, then G minus E has 1 less phase, right? Right? So now, say I was with induction, right? I started with a planar graph. Let's call this one G, planar graph G, with M edges and N vertices. Okay, so here is this one. This is G. Now okay, again, we can assume that this G is not cycle free, right? So that means it has a cycle. If it is cycle free, then it's the best case. So maybe say it has a cycle, and I take any edge here. Pick any edge, right? So pick. So I start with a G that is planar, and number of vertices is n. Number of edges is m, and number of faces, let's call this one f. Okay, I mean that's a drawing, it's a graph drawing. Okay, I don't care what drawing is it. Now consider any edge in G such that this edge E participates in a cycle. So what happens if I consider G minus E? First of all, as you guys all pointed out, that it would still remain planar. I can stick to the old drawing only. I just remove an edge, that's it. The number of vertices, of course, it doesn't change. And note that, oh, can this vertex be, can this graph G minus E be disconnected? Sujan Das, are you there?
Yes, sir.
Can you just tell what, can G minus E be a disconnected graph?
No, sir, as we are
Yeah,
as E is in a cycle, so there will be a path.
right, good. So this is something that also, if you guys should have done earlier, that if I take an edge from a cycle in a graph and I remove that edge, then this graph, other graph also remains connected. Right? The resulting graph remains connected because it's in the cycle. This is exactly how the construction of trees and all were done. Right? You keep on removing edges from the cycles till you have no cycle left, and you are left with a connected graph. Okay, so G is connected. The edges is m minus 1, that's gone down 1. And the faces, as we have discussed, will also go down by f minus 1. So I can now apply, and okay, right? So it has gone down by 1. So, and at least one cycle has been removed. Okay, or one. So, okay. So, by induction hypothesis, what do I have? F minus 1 is equals to 2 plus n minus m minus 1. Which means that if I remove this stuff, f is equals to 2 plus n minus m. And this is exactly what we wanted to prove. Right? Sorry. Or maybe I made a mistake there. Sorry, I made a mistake there. This should be m minus 1 plus m minus n. Right. And this should be therefore m minus. Doesn't matter. So this will end the proof of this theorem. Any questions over here about this statement of this form, about this proof? Any questions, any doubts? is a very important. Yeah, go ahead.
Could you please explain the last portion of this proof?
Yeah. So okay. So I got this G minus E, right?
Yes.
So G minus E is a graph, a planar graph, which is connected with these properties and have one cycle less than G, right?
Okay. Number of edges is m minus 1 because you have removed one
Exactly.
edge.
Number of edges is in 1 minus 1 because I have removed one edge.
Okay.
Okay, and number of faces is in f minus 1 because also I have removed one edge that participates in a cycle.
Yes. Okay. Then okay. It's okay.
Okay. So I'm applying the induction hypothesis.
Don't we need to do for if E does not belong to a cycle?
Sorry?
E does not belong to a cycle, we don't need that.
No, we don't need that. We are picking up the edge E in a cycle. Now, if there is no edge in a cycle, that means that graph doesn't have a cycle.
Yes.
And in that case, I am left with a tree. And that was my best case. Okay. Yeah. Okay. Now this theorem actually, so this theorem, this Euler's formula, is actually very useful. Euler's formula that is called V minus E plus F equals to 2. I always forget what is what. So best way of thinking of it is think of the tree. V is 1 more than E and F is 1. So this has to be kind of match up there. So this is how you think of it. Okay. But note that here I can get some very nice things out of here. Okay. So what is a face? If I take any face, right? As I pointed out, right, every edge participates in how many faces? Every edge participates in how many faces?
At most 2.
At most
2.
Right? At most 2. Every edge participates in at most 2 faces. Right? Good. And every face is surrounded by how many edges?
At least 3.
At least 3, right? This face is surrounded by 3. This face is surrounded by 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. The outer edge is surrounded by 1, 2, 3, 4, 5, 6, 7, 8, maybe. You can even forgetting the smaller ones, right? So every face is at least, so every face has at least 3 edges.
But what if there is a graph that doesn't have 3 edges?
Good point. In that case, okay, so we are really looking at, so I'm going to go look at only this ones which have n equals greater than equal to 3.
Okay.
Okay, because yeah, that's a very good point. Or rather, I would look at graphs for which f is bigger than 1. Let's say I will think of it. Okay, so let's consider f to be bigger than 1, strictly bigger than 1. But if f equals to 1, that means it has no cycle, right? I mean, f equals to 1 means what? Means in this formula, I get this is a connected graph where edges is exactly equals to v minus 1, which means it's a tree. Okay. Good. So maybe I should maybe just pointing out to this one as you can point it out. Let me write it this way. The f equals to 1 implies the graph G is a tree. F bigger than 1, it has two properties. First property is that every edge, every face participates in every face has more than or equal to 3 edges, and every edge is in at most 2 faces. Okay. So what do I have? Let's see. So f what is it that I want? So number of edges. Okay, so number of edges, or maybe I should just write E. Okay, I'm not writing the cardinality. That's all. E is more than equal to how much? E is more than equal to 3 times f by 2. Now why? Because every face counts gives me 3 edges. So I have this 3, but every of those edges might participate in 2 faces. So divided by 2. So the number of edges must be more than 3 times f by 2. Is this clear? Any doubt?
Sir, can you please repeat it?
Okay. So say maybe I will give you an example and that will help you. So I have said this graph, right? Now every face has 3 edges, right? So I will count the edges. I will count the edges by going over face by face. Okay. Okay. 1, 2, 3. Okay. Let me write down here. 1, 2, 3. Then I will go over here. 4, 5, 6. 4, 5, 6. Then I have go over here. 7, 8, 9. 7, 8, 9. Then 10, 11, 12, 13, 14. Okay, so 10, 11, 12, 13, 14. Then I have the last one, right? 15, 16, 17, 18, 19, 20. This is the outer edge, right? So 15, 16, 17, 18, 19, 20. So I have counted. I might have not counted some of them. Like I have not counted this thing, but I have counted each edge. And how much did I count? The total number that I count is 20, and that is more than 3 times the number of faces, because for every face I have counted at least 3. Right? Now look at it. Every edge might have been used more than once. Like this edge has been used 3 and 4. This edge has been used 6 and 7. This edge has been used 5 and 15, and so on. right? So every edge might have been used at most twice. So the number of edges therefore is more than 3 by f by 2. Is this clear?
Yes, sir.
Right? Good. So this is a very easy calculation that I'm just counting in a different way, right? So in other words, f is less than 2 times e by 3. Okay, that's it. I mean, this from here to here. So now I will do this one. So f, so I have this formula. So by Euler's formula, what do I have? Euler's formula, I have that v minus e plus f equals to 2, right? But this is f is less than this, right? So this is less than v minus e plus, I am going to use this expression, 2 by 3 e, right? So I get 2 is less than v minus e plus 2 by e 3, which means 2 is less than v minus e by 3. Or in other words, e by 3 is less than v minus 2. Or in other words, e is less than 3v minus 6. So in a planar graph, the number of edges must be less than 3 times the vertices minus 6. Okay, actually it should be kind of, I mean, this should be less than equal to, so this is less than. Now, maybe I should just ask someone. Tanmoy Shantra, are you there? Tanmoy Shantra? Okay. Who else is there? Priyabrata Mondal?
Yes, sir.
Yeah. So in a general graph, what is the maximum number of edges that you can have? Hello?
N into n minus 1 by 2. If n is the
It
number
is
of
n into n
vertices.
minus 2. So in a general graph, the edge, number of edges is less than v choose 2, which is v into v minus 1 by 2. Okay, but in planar graph, the number of edges is less than 3v minus 6. Okay, good. Now this is something very important, very useful information to have. Okay, that the number of edges is upper bounded by some quantity. Now from this, just simple fact, we can get some lot of information. For example, now let's think about this graph, K5. In K5, the number of vertices is, by the way, you should be, yeah, number of vertices is 5, right? And number of edges is 10.
10.
Is 10 less than 3 into 5 minus 6? No, right? So this one cannot be a planar graph. Okay. Now, what about this? Maybe I will just give you guys a little bit time to think. How do you prove that this graph is not so this K33. So here the number of vertices is 6 and number of edges is 9. Can you prove that this graph is not planar? Sorry.
Same thing.
Same thing? Let's see. So you mean to say that 9 is not less than, let's go over this one, 3 into V minus 6, right? 3 into 6 minus 6. But that is not true. This is correct. 9 is exactly equivalent on this. This is correct. So that doesn't disprove this planar graph.
Sir, in bipartite graph, the minimum cycle is
Good. Why don't you guys, or whoever have not seen it, okay, so just think a little bit more about this thing, okay, and try to prove it yourselves, okay. The main issue, I think your friend has kind of told that in this graph, every face. So what was the thing that we used here? We used that every face has 3 edges, right? Every face has 3 edges. But in a bipartite graph, how many edges are there in each face? Minimum? Can there be 3 edge face in a bipartite graph?
No, sir. It will create an odd cycle.
It will create an odd cycle. So for a bipartite graph, this is not 3. It is more than 3. In fact, this should be 4. Right? Now, using this extra fact, can you quickly give me, I mean, why don't you calculate it yourself right now, that in a bipartite graph, bipartite planar graph, E is less than what? Okay, let me give you 3 minutes or 4 minutes to go think. And once you're done, just maybe you can just send me a personal message about what is the value amount that you've got.
V minus 4.
Maybe you can just send a message to me instead of shouting it out. And once you have that, maybe you can try to see if you can prove. Yeah. So all of you got that? Hello.
Yes, sir.
Yes,
Wonderful. If all of you have got that, that's very good. So anyone who is struggling? Okay. So if none of you are struggling, then this good. So let me do a few things here. Okay. And okay. So good. So this is a very interesting. So how much did you get? 2 times V minus 4, right? This is what we have. And then you can see that this will prove that K33 is not a planar graph. Right. So this will have that K5 and K33 are not planar. Now, let me ask you a very simple thing now. Okay. So if I have a graph that is planar, say something like this. Now, you all told that if I take a edge, right? If I take this edge or any edge and remove it, then it is planar. It is still planar, right? So one is that removal of an edge is planar, right? I mean, not is planar, meaning removal of an edge maintains planarity. So if the original graph is planar, this is also planar. Now note that also similarly, if I remove a particular vertex, say remove a vertex. What does removing a vertex meaning? I'm removing all the edges and the vertex also. And this is also obviously of a vertex also maintains planarity. Now there is a third operation that will also maintain planarity, and this is very important. Now for understanding this one, let me ask you a simple thing. So you know that K33 is planar, right? Is not planar, sorry. But what happens if I have a vertex like this here, the two vertices here? Is this graph planar? Is this graph planar? Can somebody give me some ideas?
No, sir.
Why not?
Removal of vertex maintains planarity. So,
but if I remove a vertex, I would have removed this whole thing. And now this graph is planar. Right? You can see that this graph is planar actually.
First, we can add two edges.
Okay, I can add two edges. Which edges? Here.
Here and here. And if this is planar, then that will be also a planar. We can see that.
Why? Can you give me that? How can you say it?
Because this will contribute to face and which are not intersecting any other edges.
Okay, so let me tell you in a slightly different way what you are maybe trying to say. Okay, so say I have this one. Say this one is planar. Okay, let's say that if I add this edge, okay, then suddenly it becomes planar. Okay, let's say that. Sorry, opposite, right? So let's say that this is planar. Let's say that this is planar. Then I want to say that if I add this edge, then it is still planar. Okay. Why? Because see, if it is planar, if the original one is planar, then there is some drawing of that. There is some drawing of this graph on the plane where no edges intersects. Then I will now draw a edge from here to here by going along its edge almost, and going like this and then somehow reaching there. Right, that would not kind of cause a problem to planarity. That is kind of the high level picture that you can think of. That by adding this edge that I will not be able to do any problem. There is another way of thinking about it, and this is slightly easier way of thinking about this whole thing. Okay, say the original one is planar. Consider, okay, let this graph be planar. What does it mean? There is a planar drawing. Very good. Now, if there is a planar drawing, just think about this particular edge, this edge, just this edge, just these two vertices. Now, there's a drawing, right? Now, the edges are some edges, right? It doesn't matter how long or short they are. They are just relations. So I can therefore slowly push. I can say, oh, okay, so here this is the planar drawing, no problem. Let me remove this one and slowly move it here. I can also do that, right? My edge becomes smaller, but in that planar drawing, so maybe the planar drawing was something like this. Okay, maybe this is X, Y, and Z. X, Y, and Z. So this was the planar drawing. I'm saying, oh, so since it's a planar drawing, let me remove X, Z from here and slowly put Z over here. Now this is also a planar drawing of X, Y, and Z. Right, I have not done anything. I have just taken that edge, that vertex, and slowly kind of pulled it towards X. Okay, and I can keep on pulling it towards X till I can get this Z at the level of X. Okay, so in other words, if this is planar, then I can slowly move this Z and bring it over here. And this graph will also be planar. So think about it. So what I am doing is that I can, what is called a contracting of edges. Contract the edge and still the planarity will not be affected. Okay, so I can take an edge and slowly shrink that edge to kind of make these two edges, these vertices, these two vertices at the same place. Similarly, if this graph is planar, I can slowly move this edge, this vertex, I can go a little bit slowly and make it here. And then this graph will also become planar. So in other words, I can start with this graph, slowly shrink it and make it planar. But now I know that this graph is not planar. This is K33. So the original graph cannot be planar. Right? So if I give you a graph, and what you can do is that you are allowed to, you are allowed to either remove edges, remove vertices, or contract edges. And I have a graph G, I do this whole thing, and I get to a graph H, and somehow I know that if H is not planar, so this is either, I mean, you can apply one of those three things, right? Either you can apply remove edge or remove vertex or contract edge. If edge is not planar, then G is also not planar. Because by the contrapositive statement, if G is planar, then I know that these three operations maintain planarity, then H becomes planar. So if G is planar, then H is also planar. So in other words, if H is, G is not planar. Is this concept fine?
Sir, H is planar, but G is not planar. That is possible, right?
That is possible, very much possible. We might have contracted somewhere else and that has become planar. For example, if you now contract here these two edges, this edge, right? You will end up producing a planar graph.
Okay, yes.
Okay. So H is planar, we cannot say anything. But if H is non-planar, we know G is non-planar. Fine. And this is the beauty of it. Okay. So this is called a minor. So H is called a minor of G if G can be got from H using this set of operations: remove edges, remove vertices, or contract edges. Okay, this is called a minor. This is a very important thing. And if you are interested in learning graph theory later on, you realize that this is a very beautiful subject called graph minor theory. It's called. Okay. Now, important thing is that I know that K5 and K33 is not planar. So I know, so I can say this is a theorem. Therefore, that if so, right, if G is sorry, maybe I should write it this way. G has K5 or K33 as minor implies G is not planar. Is this theorem clear? I mean, the proof is something that we almost discussed here, right? If you can shrink G, shrink or remove edges and remove vertices and get K5, the idea is that, okay, if you are drawing G on a plane, then somehow or other you are actually ending up drawing K5 on a plane, or you are producing K33 as a plane. In that case, I know that G cannot have a planar drawing. Any comment about any doubt about this particular whatever has been written till now? Okay.
The other way around, is it true?
Yes, the other way around is also true. This is an if and only if, and this is called a Kuratowski's theorem. Kuratowski's theorem. Now this is a big result. Many times I do cover it in class, but this time I'm not covering it in class, the proof of it at least, because I don't have time for that and it's a bit involved. So giving this presentation online is very hard. I still will encourage you guys, whoever is interested, to take a look at this one, but at least remember this theorem statement that a graph is planar if and only if G does not have K5 or and K33 as minor. Or in other words, if G has K5 or K33 as minor, then the graph is not planar. And if G graph is not planar, it must have K5 or K33 as minor. It's a massive theorem. It is completely characterizes what is a planar graph.
So when
Okay.
using the T and H, so there also is the reverse also true. Like if G is not planar, then H is also not planar. Is that also true?
No, that is not true. That is not true in general. As I told you, right? So for example, this is non-planar, right? But if I now shrink this edge, the resulting graph becomes planar. See, of course, if I keep on shrinking edges, I will get a constant, empty graph, right? Which is planar. So every graph can be shrunk and get an empty graph. So so if you start from a, so what it says is that if you start from a, I mean, in something you can write it in this way. If G is non-planar, then there is a set of contractions that you can do in which H becomes K33 or K5. Okay, that is what the meaning of this theorem is. So do remember this theorem. This theorem and this way of proving whether something is planar and not is something very, very fundamental to the concept of graph theory or planar graphs actually. Now this is I mean, this whole area has been developed into this whole area called a graph minor theory. And I will not go into that details here, but it is something that you might really want to take a note of. Okay, at least this theorem and this. Okay, so I think I will stop now if you have no questions, but I'll leave you with a problem and another thing. First of all, can you prove, so this is something I want you to try, prove that a planar graph has a vertex coloring using six colors. Okay, so prove this step. With whatever thing that I have done today, you should be able to do it today. It should not take too much time. And this is a good exercise to have for you guys. Also, tomorrow, if I'm not wrong, you don't have anything at 12 o'clock, right? Or 10 o'clock. When was the programming course?
10 o'clock onwards.
10 o'clock onwards. So is the programming course going on? Or is it over?
It's over.
Okay. So then I suggest that we have tomorrow's class from 10 to 12. I will not take a class at 2 o'clock. Hello?
I said tomorrow we have a CO class from 10 to 12.
Is it there?
Sarah mentioned it earlier in the Monday.
Okay. Tomorrow there is a CO class from 10 to 12?
Yes, sir.
Just let me, just give me 2 seconds. Let me kind of confirm with some phone. Just one second. হ্যালো, হ্যাঁ কালকে তোমার সিও ক্লাস আছে সকালবেলা 10টার সময়? নেই তো, তাই তো, সেটাই আমি স্টুডেন্টরা বলছিল। ঠিক আছে, ঠিক আছে, থ্যাংকস। আচ্ছা ঠিক আছে, আমি ওকে, পারফেক্ট পারফেক্ট, ঠিক আছে। হ্যাঁ হ্যাঁ, আমি এটা নিয়ে যাবো, ঠিক আছে। সেটাও তো মানে করেন, ঠিক আছে, আমি পরে বলছি। হ্যাঁ আচ্ছা আচ্ছা আচ্ছা, ঠিক আছে ঠিক আছে, চলো। হ্যাঁ আমি, yeah, hello. So there is no CO class tomorrow at 10 o'clock. So I will have a class tomorrow at 10 o'clock. Okay. Tomorrow 10 o'clock we have a discrete math class, and at 2 o'clock there will be no discrete math class. But if you guys are interested, I can ask a TA to take discuss some questions, something like that. Okay. I mean, it's not necessary, but if you are interested to discuss some problems, some solutions and whatever, then it can be done. Okay, any questions? Hello. Hello. Am I audible?
Yes, yes.
Okay. Okay, so we will meet tomorrow at this one is gone out now. We'll meet tomorrow from 10 to maybe 11:30 or something like that. And you guys, in the meantime, try to solve this particular problem. Okay. So most likely tomorrow also will be the last class that I will take. I will not take any extra class on Sunday or something like that. Unless you want to discuss some questions, clear some doubts. In that case, I'll be happy to organize some tutorials or some discussions and all those things. But yeah, so the exam will be of 100 marks. I have given I have submitted the question paper, and I can say that it is not hard, but it is not easy either. If you have followed whatever stuffs have been done in the class, and if you have solved the exercises and problem sets that have been given, you should not have any problem. Okay. One thing that I will, yeah. So I assume that all of you will be coming to coming to campus by then, right? Or is there anybody who will not be coming to campus?
We'll be coming, I guess.
Yeah, I think that's yeah. Good. So I guess I will see you guys all physically during the exam only. Okay. Yeah. Yeah.
Exam will be of 100 marks.
Exam is of 100 marks. Exam is of 100 marks. Yeah, and then it will only be contributing. Yeah, I think 40 marks to the whole thing. And the internal assignments, the internal scores will contribute to the remaining.
Hello, sir.
Yeah.
Sir, can we submit a handwritten assignment for this upcoming assignment? Handwritten solution.
Okay. I mean,
LaTeX is taking a lot of time. Writing on
okay.
LaTeX.
I mean, sure. I mean, if that is really something that is bugging you, okay, go ahead.
Thank you, sir.
But I thought that by now you should have got used to LaTeX.
Yes, sir, we can write, but this takes a lot of time, and exam is coming.
Okay, fine. Sure. Okay, but in that case, please write every question in a separate paper. Okay, and write the first question in the first paper, second question in the second paper, third question in the third paper, and then submit accordingly. It should not be that, okay, because particularly you will be scanning it and uploading it. So somehow problem number 4 is hidden. That is very hard to find out in the in this online setting.
Okay, sir.
Okay. Okay, good. So then let's stop the class today. Okay. So see you tomorrow at 10. Bye.